So now we'll be discussing how orbitals overlap to make covalent bonds, because in covalent bonds you have we generally represent shells sharing electrons. All right, but today we'll be discussing how those electrons are shared between orbitals, and we're going to start off with the hydrogen molecule. So if I have a hydrogen molecule, what do I know about that? I know that two hydrogen atoms have overlapped. Okay, and in O levels we just draw the shell diagram. Now you might see it drawn like this. Okay, hydrogen has one shell, hydrogen has one shell, and they're overlapping. The problem is I'm not showing you the shells here actually, because hydrogen's outermost configuration is only one electron, it's 1s1. So when I write hydrogen's each atom's electron configuration is just literally 1s1, right? So what happens in hydrogen, and this is something that is true for all covalent bonds, is that for covalent bonds to overlap, it's actually orbitals that overlap. So not shells, but orbitals overlap. And orbitals overlap to share a total of 2 electrons. Okay, generally speaking, how does that happen? If an electron in box diagram represents an orbital, you have to have one orbital overlapping with the other orbital, and the electrons are shared, they'll be in opposite spins. They don't have to be in opposite spins initially, but when the two orbitals, let's say this is hydrogen's orbital, this is 1s and this is 1s. So when these are shared with each other, because I'm making the orbital in electron box diagram, so we identify, okay, the 1s basically is the orbital that has only one electron, that orbital gets shared. Hydrogen is only one, so it's pretty simple. So this overlaps with this. So basically a 1s orbital overlaps with a 1s orbital, and that results in this kind of shape. So instead of the shell overlapping, in hydrogen the 1s orbital overlaps with the 1s orbital, and in the middle is your region of orbital overlap right there. And so if these electrons are shared individually, you know, there must be here somewhere one electron there, one there, but when they're shared, they both go in this region of space right there. So both are right there in opposite spins, and this is how orbitals have overlapped, and the shared electrons are found somewhere in between. So what just happened? Basically this, that hydrogen atoms that had one electron in each of the 1s's, they end up overlapping, and this overall oval represents the molecule, but the electrons are mainly found dead center between the two hydrogen atoms, shared space. And this is the 1s orbital overlapping with the 1s orbital, but the shared electrons are somewhere in the middle. So instead of shells overlapping, we have electrons overlapping. So even if you draw them in the same spin or opposite spins, the moment they overlap, they will be in opposite spin. So if they're in the same spin, the molecule or the atom just has to turn itself upside down and it'll become opposite spin, right? So even if they're the same spin, the atom will turn itself in a way that they'll become opposite spins, and then they overlap. Because initially when we draw atoms, we always draw the up first. So on its own, it's how we draw the spin. But in the end, you need to know that is that in the overlap region, the electrons are in opposite spins. This overlap region behaves like an orbital. It has a maximum number of 2 electrons that can be shared. Anytime one or two orbitals overlap, their shared region is 2 electrons only. Now, in O levels, you've done single bonding and double bonding and triple bonding, right? And a double bond has 4 electrons, 2 shared each. So that becomes a little complicated how that happens, and we'll get to that in a minute. But this is what we call a head-on overlap. Yeah, this is a head-on overlap, and the electrons are shared in the middle. We'll see many more types of this right now, but just wait on that. First, I want to show you because what are orbitals? There are regions where we're going to find the electrons. So if I give you an orbital density map, you know the dot maps that we had for orbitals, how will that differ for when it becomes a molecule? This is how it becomes. So you got these dots represent the electron, the 1s electron. And remember, the boundary of this, where there's a 95% chance of finding the electron, is called the 1s orbital. So this is one hydrogen atom, and this is the other hydrogen atom. And when these two atoms overlap, they become a molecule. This is the H2 molecule. Okay, and now instead of each electron being all around the atom, the electron is mostly, the two electrons are mostly found in the center. You'll see how dark this region is now because of density wise of the orange dots. Here they spread out. Now they are concentrated between both the atoms. So this is your covalent bond. If you're wondering where the bond is, basically the H's have a nucleus each. And so that positive nucleus is pulling these electrons, one towards the left and one towards the right. And that pull is your bond. And basically orbitals overlapped and the electrons are now shared dead center, basically. All right. So this is how a hydrogen 1s orbital overlaps with another 1s orbital to have the electrons in this shared region. So this shared region is where these electrons are now. And this is one way you can have electron overlap, where the electrons in an s orbital with another electron in the other s orbital overlap to be shared. But this is how s and s overlap, because you need to understand that when electrons bond from the valence shell, it's not just going to be s bonding with s, it's going to be s bonding with p and p bonding with p. Now let's say we want to talk about hydrogen and fluorine reacting. You know, hydrogen and fluorine make a certain bond, right? And a hydrogen atom has, it's a 1s1 configuration, and a fluorine atom has 1s2, 2s2, 2p, 5 configuration. Before we even talk about orbital overlap and how these guys make a bond to form HF that we knew to be this, having a single bond, and we in O levels we draw shells overlap. Now we're going to talk about how do orbitals overlap, because that's really what's happening. So what we're going to do is find the orbitals that are going to overlap. First of all, it's very easy to find the orbital that will overlap in hydrogen. It'll be the valence orbital having only one electron. That's the only one right here. So the one I'm going to highlight right now, this fellow, is the orbital that's going to overlap with something in F, meaning another orbital in F. Now the orbital it can only overlap has to be from the valence shell, and the valence shell is 2s and 2p. Now when I look at 2s and 2p, which of these has an orbital that has only one electron? That's the only one is right there. Now they might have been drawn in the same spin, but once they overlap, they have opposite spins. And it's basically this 1s orbital with this 2p orbital. And this is x, y, and z. And remember, the axes, before I show that to you, is that most people think that only the horizontal is x and the vertical is y, and out of the board and into the board is z. You could actually rotate this and have x vertical, y horizontal, or you can turn this 90 degrees here and you get the z horizontal and the xy out of the board. Meaning I could have written it like this also. So out of the board and into the board. Let's call that x, vertical is y, and horizontal is z. So basically it's this z orbital, that horizontal in this diagram, is going to overlap with the h, s orbital. How will it do that? Very simply this way. So you're going to have the 1s of the h overlap with the 2p z of the f, and they have one overlap region right here. And this overlap region is where both the electrons are going to be, being pulled by this nucleus for hydrogen and this nucleus by fluorine or fluorines. But they are going to be found dead center. And this is 1s overlapping with 2p. And some of you might wonder, well, why did the other 2p lobe become smaller? Well, after overlap, there's a fewer chance they'll be found here. So that area becomes smaller. But our concern will be the overlap region anyways, because that's where the greatest chance of finding the electron will be between the two. So this would be how hydrogen and fluorine overlap. It won't be the shells overlap. It would be the hydrogen's 1s orbital will overlap the space with the 2p z orbital of fluorine to make HF like this. You can have it overlap horizontal. You could have also done it vertical, meaning if Z was vertical, it could still be possible. Let me show that to you. So first I gave you how 2s would overlap, 1s of hydrogen with the 1s of another hydrogen. And honestly speaking, covalent bonding can only be found in nonmetals, and there are only a handful of nonmetals that react. You got hydrogen, which has the electrons in the s orbital, and every other non-metal is either in groups 5, 6, or 7, or 15, 16, 17, 18. Groups 18 don't react, they're noble gases, so all you have left is group 7, which is 17, 6, 16, or 5, 15. And if you remember, 5 has p3 configuration, 6 has p4, and then p5. So every other non-metal has only the p orbital interacting to make bonds. And silicon and carbon, which has again p orbitals filled up, so they interact. So the only s orbital interaction is by hydrogen. So hydrogen, first of all, is the only non-metal that you know of that has s orbital bonds to make. Because it's the only non-metal that has one electron in the s orbital. And so that was right here. And fluorine is one example of having an unpaired electron in a p orbital. We call these unpaired electrons. So we're going to look for orbitals that have unpaired, singly filled electrons. And unpaired electron orbitals are the ones that are going to overlap, and that's where the overlap electron region will be, right there. And the overlap can be like this facing horizontally. You could have had the p vertically also. So you could have had a horizontal overlap like this, or the VP was vertical and the overlap could be on the top lobe or the bottom lobe. It doesn't matter. They're all the same, because you can turn any of these to 90 degrees. You turn this 90 degrees counterclockwise, you'll get this. You turn this 90 degrees counterclockwise, you'll get this. Yeah, this was clockwise, counterclockwise, but you get the point. So this is the second way of having orbital overlap. Again, so the first one was two s's, and this one is s and p overlap. That should lead you to the third question. Well, wait a minute. Then how do p and p overlap, right? Now, before I do this, if you guys can absorb this, if I were to show you all the electrons of fluorine, like, yes, here we only drew the orbital that was empty, this one. But let me show you all the p electrons of fluorine and then make a bond with hydrogen. We don't show that to you guys often in books because it becomes confusing, but I'd like to show that to you.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
So here I've tried to draw a fluorine atom's nucleus with its px, py, and pz. Now, for the sake of argument, let's say the one coming out of the board is your x, and the one that's vertical is your y. And x and y have two electrons each. And so the one z that's horizontal, that has only one electron. So when fluorine overlaps with, what's his face, hydrogen, now hydrogen's electron is in just a 1s orbital, right? So now let's say this is that 1s, hydrogen's 1s orbital, and that has only one electron too, and that comes and moves right here. So this is hydrogen, okay, and it comes and overlaps right here. It has its own electron too. So now that's two electrons being shared, okay. Hydrogen electron in the s orbital overlapping with the pz. So this is 2pz, 2px, 2py. All right. The position of z, y, x could be any. This could have been called y, because if you take any axis and you can turn the whole thing, it's like a cube. Turn it, it'll become the same thing. So y can become z, or y can become, let me say, horizontal or vertical, or out of the board into the board. Z can become all of that. So it's how we label them, basically. So this is how the S of H overlaps with the PZ of fluorine, or any P. That's why we don't even care PZ, P, whatever. It's the same. All right. So let's say two fluorine atoms want a bond. Now, this is the electron and box diagrams of the two fluorine atoms. Now, obviously, you can identify which orbital is going to want to overlap, right? It's going to be the one that is only singly filled or unpaired, that has unpaired electrons. And which has unpaired electrons? In this case, it seems to be the 2p Z again. So let me highlight that for you. This one and this one. These two will overlap with each other. So here is that happening. 2pZs horizontally come together and one of their lobes overlaps with each other. That's right here. Because that's the fastest way to overlap. And that overlap region is where you're going to find these two electrons, basically. Yep. Now, what's happening is this. Let me show this to you. So here, I've actually tried to draw the fluorine atom's nucleus. And for that matter, this is fluorine and this is fluorine. And for the sake of argument, I'll group this together and group these guys together. Okay. So now, what I want to show you is that how does this one of these overlaps with the. So one example is, and I'm going to zoom out here. So one way is this, and pay attention, is that you could have overlap like this. Let me repeat that. So forget the electrons right now. Let's just talk about orbitals. Assuming that the orbitals overlapping have only one electron. So this is how p and p would overlap right here. And you're going to now find the two electrons shared right in this region. But they don't have to overlap horizontally. You could also have overlap like this. There's no rule against that. So this is the same thing, identical. In fact, let me try to move this. Let me move this on the side and show you that this diagram, or for that matter, this, I'm just duplicating that, sorry. So here we have, both of these are the same thing. They are sharing electrons in this highlighted region of space. The two shared electrons are right here. You know, you could draw it horizontally, you could draw it vertically. You might say, well, what about in front of the board, behind the board? You could do that too, you know, and that's absolutely possible. The vertical orbitals can overlap, the horizontal orbitals can overlap, even the out of the board and behind the board can overlap. The idea being that this guy will approach this guy from the backside, if that's possible to show. 3-dimensional is hard to show, so it might be very tricky, but that's what I'm saying. This is going to come from behind it. So in fact, this one is even behind this one, basically. Let me see if I can show this to you otherwise. Here, you know, like that. Yeah, like that. So it's like that, you see? And yes, these are behind, they're not overlapping. The only one is overlapping is right here. And so PZs can overlap, the verticals and horizontals. For the exam, all you gotta show is the P overlapping with P. And every book draws P differently. You could have shown this simply. You don't even have to make this smaller. It's just simply take this, overlap with this. So for the exam, this is what you draw, by the way. So for the exam, you want to show P orbital overlap is all you will be asked to draw. Overlap, independent of any other orbital. So you will draw one P like this, and literally just like that. And you can say, my diagrams pretty suck, but that's why I draw them beforehand. This is your P and P overlap. You want to draw for the S and P overlap, this is S and P overlap. Well, you can also draw them vertically, which sucks for me, but you can do that also. You can draw both of them vertically also for the exam. But you guys get the idea. These are ugly, so I'm going to remove them from the picture and image. This is what they expect you to draw in the exam. Literally just this and nothing else. To show S and S orbital overlap, and that's the overlap region. S and P overlap, one overlap region. P and P overlap, one overlap region. Basically, when S and S overlap, they'll have only one region of space overlapping. That's the pink one here. S will overlap with one of the two lobes of P, not both, just one of the two. Not in the middle, just one of the two edges. That's like this. One area, and it's an area right dead center between the two nuclei. And when P and P overlap, only one of the two lobes overlaps. It's easier to draw horizontal P than vertical P, hence, but you can draw it vertically also, but as long as only one overlaps with one. And this is what you draw for the exam, right here. S and S overlap, S and P overlap, S and P and P overlap. This is S and S overlap, S and P overlap, P and P overlap. And basically, these are what we call sigma bonds. So when your orbitals overlap like this, you call them sigma bonds. Now, sigma bonds will not make sense unless I show you the other kind of bond, which is pi bond. But that's coming up. First, let's just talk about these three overlaps. So S and S, these are all single bonds. Two pairs of electrons being shared between two nuclei. Two electrons. So this is an example was H and H. This example was H and F. And the last example was F and F. It doesn't have to be F and F, could have been Cl, Cl, ClF, ClBr. Anytime p orbitals overlap. And H and F overlap, it could be HCl, HBr, HI. Could also be H and O because O has p orbitals too. Anytime you, because the only two orbitals that are going to be involving themselves in covalent bonding are S and P. That's why we don't even study D and AS. It's just going to be S and P. And so the most basic kind of bonds are sigma bonds. This is how they are formed. So sigma bonds are a type of a covalent bond because a covalent bond can be both a sigma bond and a pi bond. All right. We'll talk about pi in a second. The Greek symbol pi, this is Greek symbol sigma. Sigma is the Greek letter for S, hence, and this was first found in S orbitals. That's probably why they named it. But S, I don't know why. It's just called a sigma bond. That's our name to it. So when chemists say sigma bonds, they're saying either S and S are overlapping, S and P are overlapping, or P and P are overlapping. There are other kinds of sigma bonds coming up a little later, but for now, you only need to concern yourselves with that only S and S, S or P and P overlap. So basically, this is how all single bonds are made. Every single bond is a sigma bond. Everywhere you've ever seen a single bond, you've seen them in these molecules, C and H, H2O, ammonia. All those single bonds are all sigma bonds. S and P, S and S, P and P overlap. But we also know that we have double bonds for things like you got what you call it, oxygen, right? Now oxygen has, we know it has this layout. We did the dot and cross earlier. It is a double bond. So how do double bonds form? Because double bonds are not so straightforward as single bonds. And to understand that, we have to look at the electron and box diagram for oxygen first. So this is what we have. This is the electron and box diagram for each oxygen. There are two of them, right? So according to our orbital overlap theory, basically these two orbitals that I'm highlighting are going to overlap with each other because one electron, one electron, one electron, one electron. And technically speaking, these two will overlap, the two yellow ones that I've highlighted, and they will share two electrons. That's the first of the two bonds. And this is going to make the second bond. Hence, you have a double bond. But in terms of orbital overlap, how do I show this? Because it's easier to see in electron box diagrams, but how do I show this in orbital overlap? Yeah. So again, I'm going to show you diagrams for all the oxygen electrons of oxygen. Again, you don't have to draw this for the exam. This is just for understanding. For the exam, it'll be a much simpler diagram. And I'll focus on that in a bit. So let me first erase this. I don't need that anymore. Yeah, because it's just bothering me, the line. It's an ugly line. So remove that. And now, so what's going to happen? So here I have made for you just again the p orbital because the s are not involving themselves in bonding. So let's assume that this, the unpaired here, and so the paired here and paired here are these ones. So for example, this yellow orbital highlighted, let's say your horizontal one. Let's say. So this is your yellow highlighted. You know, in both, these are oxygen atoms, obviously, right? So I've got oxygen in the middle. This is the oxygen nucleus. All right. This is the nucleus. All right. And these have one electron each. So one here and one here. I'm using dots. Okay. Obviously, the one that is not bonding has already two electrons. So the ones that, this one is your X. This one. X. Y. And Z, whatever you want to call them. X, Y, and Z. I've drawn it this way because this is easier to explain. So I'm going to, okay, one second. Group this. And I need to just group this, all of this. Sorry. Group that. Yeah. All right. So, oops. 1 second. Yeah, now this makes sense. So I got a hydrogen oxygen atom here and oxygen atom here. All right. And I need more space. So I'm going to remove that and bring them down to play a little more cleanly with them. So far, this is me showing you the electrons in the P Y having 2. And remember, PZ having 2 also. Sorry, 1 also. So this is your P, let's call it PZ having, or PZ having 2 electrons. 1 electron each, not 2. Sorry. So let's say 1 electron here and 1 here. For now. Okay. So the idea for this is because you see, the goal is that the Px, and I will try, and if I can do that, show you the box diagram again, just for a minute, so that we can all get on the same page. So, all right. Okay, just 1 second. The diagrams are complicated to move around. So I'll just bring them down again, actually no, up again, and scroll up for a second. So what I wanted to show you was that the 1s, the 2s, and the 2px is not going to bond. The 2px is this one that I've not even highlighted. And here also, it's only the 2py that has 1 electron each, and 2pz that has 1 electron each that are going to overlap. I have put the electrons here for a reason, just ignore them why I've done that. Our concern is only orbital overlap, really. So now, first of all, they have to share these two. So the first time this happens is O comes closer and closer and makes the same overlap we have just been doing right now. We have been doing this overlap earlier, just now. And this is the PY, the yellow one, PY overlapping with this PY. PY overlapping with PY. All right? So PY with PY this is that overlap. Now this is the one overlap. But the ones I've highlighted in green also have to overlap. How do they overlap? Their angles cannot be changed. They have to be perpendicular to each other. So it's not like I can take this guy and make it turn. Because if I start making this turn, let's say like this, to bond this way, it can't happen. This is not going to happen like this. They have to bond head on. So I'm going to undo this and bring it back here. And now, how do they bond? So what happens in reality is that these two can only bond getting closer and closer this way. So what starts happening is they start overlapping this way, this region. So this starts getting fatter and fatter, and they start overlapping this way. How? Let me show that to you. So you got to use some imagination here because it gets confusing, which is why no book has this diagram. What happens is this. They get closer and closer and closer and closer. And yes, it might seem confusing with the other orbitals around it, but if you can ignore them for a second and see what's happened to the green orbitals. And the vertical ones, the green ones, overlap right here and right here. Obviously, my scale diagram is not drawn to scale because the nucleus is not that big. They don't overlap. But what's happening is, let me show you again. So what's happening is that there were 2 electrons here, okay, that end up being shared. Why is this electron there? Oh, my bad. Yeah, that. So this was like this, and it got closer and closer, and the only thing you should really worry about is the green one right now. That's going to overlap like this. Obviously, it can't get this close, so it kind of becomes like this. And all of this region becomes green. The orbitals become larger. Their overlap is even much larger. They expand and engulfs. So they get closer, and they, in fact, take more space. So they become larger. The combined region becomes much larger. For the exam, we show it simply, and I'll show that to you in a second. For the exam, this is called, by the way, differences. This is called a pi bond. Before the exam, I'll talk about that in a second. This is called a pi bond, the Greek symbol. And the pi bond is not just one area of overlap. It's 2 areas of overlap above and below the nucleus. And the yellow region is your sigma bond. So in a double bond, the first bond is sigma, and the second bond is pi. Sigma is between the two nuclei, pi is above and below the nuclei. Together, the pi is definitely going to be much larger space, because only 2 electrons shared in this larger space, their density is lower. And so that's what a pi bond is. Let me show you what you have to draw for the exam. For the exam, this is what you can show them. This, literally like this. You show them in the vertical piece overlapped. We call this a lateral overlap, while this was called a head-on overlap. A head-on overlap, a lateral overlap. Sigma is a head-on overlap, while pi is a lateral overlap. And pi can only and only be made with p orbitals. S orbitals will always make sigma. And p orbitals can make sigma and pi. So sigma are for S and S overlap, S and P overlap, even P and P overlap. So P and P overlap can make sigma and also make pi. So in oxygen, the P and P overlap did make sigma, but the P and P overlap also made pi for the second bond. Now, if this is your fine overlap, this is where your sigma bond is, right in the middle, right there, the 2 electrons, and that's your pi bond. And what I was saying about density was, this is a better understanding of the density, is that you had the 2 nuclei at the end of this line. The stick represents the sigma bond, while the dots represent the pi bond. That's where the pi electrons are. So in oxygen, this is what you would think. Sigma bond, and this region above and below contains your pi bond. This is how you draw for the exam. Pi, sigma. Remember, the pi is combined both regions together. So the 2 combined regions are 1 pi bond. And the line is sigma bond. So the lateral overlap, which is a sideways overlap, lateral means sideways. It creates 2 regions of overlap. That's a pi bond. The head-on overlap is a sigma bond. This ends the conversation about basic sigma and pi. We look at more examples of pi, but this ends this one right here, this conversation about the example of oxygen. All right?
Hey there. If you found this A-Level Chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-Level Chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-Level subjects. Thousands of students have already taken the leap. What are you waiting for?